So continuing the podcast number 17, in this one we're going to collect hydrogen gas through this chemical reaction. And chemical reaction, as it bubbles through, in addition to the hydrogen gas, you end up getting water vapor mixed up here. So what that means is you have to take into account the water vapor and the hydrogen gas together will add up to the total amount of pressure in the room, 700 millimeters of mercury, as we can see this. So since it's telling us that this number is 25 millimeters of mercury for the water, that must mean 25 plus X is equal to 700. So we can see that the answer is C, 675. So here we have this case of effusion of gases. Effusion, if you can imagine a box, and of this box you've got a little hole in the box like this, and so then you have two types of gases in here. One is going to be oxygen, according to this problem. The other is some unknown gas. But we know that the unknown gas has a lighter molar mass because apparently these gases, as they escape through the hole, this unknown gas can escape at 4 times the rate of oxygen. Well, we know the molar mass of oxygen. They tell us what rate 1 is. So let's say rate 1 is the oxygen, and M1 is the molar mass of oxygen. Then this unknown gas, X, is at a rate 4 times this. So we can do a little bit of math. We could say that 0.10 over 0.40, which is 4 times the 0.10, is equal to the square root of the molar mass of the gas we're looking at over 32 grams per mole for oxygen. Solving this out, we find out that the actual molar mass of the gas is 2.0, and it is hydrogen. So equal masses of helium and neon. So if you think about it, helium and neon is quite a bit heavier than helium. It's about, for every, say, 2.5 moles of helium, you'd have about 0.5 moles of neon. That's just the same ratio, given the molar mass of this is 4, the molar mass of this is about 20, so it's about 5 times more. That means if the total pressure is 12 atmospheres, and if you divided this up into 6 equal parts, 1, 2, 3, 4, 5, 6, the pressure of the neon is only 1/6 that of the total, and 5/6 of it is going to be the pressure of the helium. So out of 12, assuming, like, say these were all 2 atmospheres, dividing the 12 up into 6 pieces, then helium represents 4 atmospheres, so the answer should be B. Okay, here we're continuing on. This is kind of a tricky one. You have this combustion of this hydrocarbon, X. Here are the several of the formulas that are possible. It combusts in oxygen, but all we know is that 0.30 atmospheres, so this is in pressure really, of carbon dioxide gas is product, and then 0.40 atmospheres of water vapor. Now, the amount of pressure given off here is directly related to the number of moles of gas given off. So we could say the ratio here of gas given off could be 0.3 to 0.4. So if we just pretended like this is actually moles here instead of atmospheres, it gives a pretty close approximation. So looking at some of the possibilities here, you could put these formulas in and then solve for the ratio, one thing I thought was that if it was, for example, C3H8, which is this one right here, let me clean that up a little bit for you. Okay, so if the answer was C3H8, and you could go through and do all of these this way if you want, then I noticed that I have 3 full C's here, but I have only 1/10. So if I divide, say, both sides by 1/10, I get this, and I divide this by 1/10, I get 4. So this works out nicely to be C.3 H.4, if you look at it that way, would give these same numbers over here. Maybe I didn't describe that too well, but it's just a matter of balancing it out. That would give the correct answer to be C. So here we have these two gases, and according to the above, which remains in the reaction vessel. Okay, so if we have equal masses, okay, that's what I'm looking for. So we have equal masses, so let's say we have, you know, let's go 10 grams of hydrogen and 10 grams of oxygen. Well, oxygen is way heavier than hydrogen. This is only 2 grams per mole. This is 32. So if we have equal masses, we're going to have a lot of excess hydrogen, and this is going to be completely wiped out, meaning that we're going to have in the reaction vessel, well, let's see now, we're going to have, so we have 10 grams of this, and we have, say, 10 grams of that. We're going to have way less moles here by a considerable amount. So it would seem to me that we're going to have extra hydrogen in the answer and extra water vapor. Since the equal masses, we should have a lot of extra hydrogen available. So we have water because the making product, my guess is the answer here is probably B. And we'll have no oxygen at all. Now 22, we have this reaction happening where we have 1 mole of this creates 1 mole of that, 1 mole of that. The initial pressure is 1 atmosphere too, here. And so if the reaction were to go to completion, the total pressure in the container would be, well, notice that these molecules are breaking up into 2 pieces. So it makes sense that if the before picture is we have 1 molecule, and in the after picture we have 2 molecules of these different gases, well then you would think the pressure here should double, because now you've got twice as many particles in the same 1 liter container. So if it started out at 1 atmosphere, well, logically it should end at 2 atmospheres. Okay, now this problem down here, number 23, a colorless gas. So that would preclude, it could not be chlorine, that's yellow, or bromine, that's brown. So those are ruled out. And it seems that when you put it into a bottle, the splint goes out. So it can't be a gas that's flammable. It can't be oxygen or hydrogen. It really would have to be nitrogen, which is a fairly inert gas. Okay, so in this slide we have at room temperature 1 atmosphere, the molecules are furthest apart in. So it turns out gases have the particles furthest apart. So as I look at this, mercury is typically a liquid at 1 atmosphere in room temperature. Water is typically a liquid also. Iodine is actually a solid. Bromine is actually a liquid. Fluorine is the only one of these choices that's truly a gas at these temperatures and pressures. So certainly the molecules are furthest apart in fluorine, being it's the only gas that's mentioned here. So what is the name of the process? Solid to gas. So going from a solid to a gas without turning into a liquid is called sublimation. Just a definition. So here we have methanol burning to form carbon dioxide and water. What volume of oxygen is required to burn 6 liters of gaseous methanol? Okay, so writing out this formula just might be smart to balance it first of all. Something might turn up as we do that. So a typical combustion reaction looks like this. See 1 mole of that makes 1 mole of that. We've got 4 hydrogens, so let me put a 2 here. And so hydrogens are balanced. Now we have 4 oxygens over here, 2 and 2, so 4 oxygens. Here I have 3 oxygens. So probably we're going to need to double these and double this also. Now that gives us 2 oxygens here, but 4 and so we have 10 oxygens over here. 2 means I have to have 8 oxygens. Let's see, no, I have 4 oxygens and 4 oxygens. I miscounted. This is only 8 oxygens over here. So 8 oxygens means I have 2 here. I need 6 here. Okay, so it turns out that the amount of oxygen, the volume required would be a 3:2 ratio. So assuming that the amount of liters of oxygen, I guess we could convert that to moles, knowing, but it doesn't give us any information about temperature and pressure. So the best we can do here is just say that if we start out with 6 liters of methanol, no doubt it's going to react on a 2:3 ratio. And we're going to need this number of liters of O2. So in other words, 2 liters of methanol create 3 liters of O2. So just simplifying this, it appears 3 times 3 should be 9 liters of oxygen would be required. I think that's probably the correct way to look at that. So gases tend to exhibit non-ideal behavior under conditions of, well, when they're really tightly pressed together and moving slowly, that's when they tend to exhibit non-ideal behavior. Ideal behavior is when the particles exhibit no attraction. So under conditions of high pressure and low temperature would be the case where it's most non-ideal. So in this case the answer is B. And finally, these last 4 problems, what increases in a gas as it's heated? Well, obviously the gas goes up in pressure and kinetic energy. So this is the definition of temperature here. And of course, as gas, if you don't allow the volume to expand, then the pressure has to go up as the particles are slamming into the side of the container harder and harder. That builds up the pressure in here. So it seems like the answer is 1 and 2. How many moles of gas are present in a 10-liter sample? Well, this is kind of an easy. At STP, you have 22.4 liters is 1 mole at STP. So how many moles of gas are in a 10-liter sample? So if I start out with a 10-liter sample, and I divide by the 22.4 is 1 mole, you can see I'm going to get a little bit less than 0.5. So if I look over at my answers, I can already see that B is coming out is the correct answer. So Avogadro's law is basically when it states that the moles of a gas are directly proportionate to the volume of a gas. So it seems like the answer would have to be N and V, C. So here we have a gas law which states that the pressure is directly proportionate to the temperature, like this. And so if that's the case, then if we start with 3 atmospheres and the temperature is 30, we increase the temperature to 60, so then we're solving for this. In order to keep this correct, this would have to go up to 6 atmospheres, which would be A. Okay, so that's the end of the podcast. Hopefully this was helpful as a general review.